Okay, kids, we're back. I got my coffee, I got more energy, I'm ready to rock and or roll. I like doing both, okay? Not rocking or rolling, rock and roll. That's the way to go, way to go. Now, let's do a problem using the heat equation. We just did one in the last video. I know, but we're gonna do a more complicated problem. That is not the attitude we want, young man, not the attitude. Okay, so what we're gonna do this time is use this heat equation, but for a problem like this, it's a better problem. Winky, 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 better problem. Let's say that we have, let's see, we'll put it over here. You can see over here, you can see over here, okay. Let's say we've got this, maybe it's a styrofoam container. Styrofoam works great as what's called a calorimeter. A calorimeter is something which limits the amount of heat in and out of a system, to isolate the system, to keep the heat in, and only let the system do the stuff that you need to do. Okay, calorimeter. And you've got a calorimeter that's got some water in it, which we know is a great heat absorber. So we've got some water here, and let's say there's 500 milliliters of water inside that calorimeter, and you've got a chunk of aluminum, and you're going to take that aluminum, it's hot aluminum, hot, don't touch it, don't touch it, and let's say it's at 100 degrees Celsius. My water in my calorimeter is at nice room temperature, 20 degrees Celsius. 20 degrees Celsius. And we're going to take this chunk of aluminum, and maybe it's, let's say, 300 grams of aluminum. So 300 grams of aluminum, I want to put it in the water. Okay. What's going to happen to the temperature of the aluminum? Come on, you know, it's going to go down. What's going to happen to the temperature of my relatively cool water? It's going to go up. Now, there'll be a point where the temperatures eventually meet, and that's called equilibrium. When the temperature of the aluminum and the water inside the calorimeter are equal to each other, the same, we have equilibrium, same temperature, equilibrium. Our task is to figure out what is that temperature going to be at. What is the equilibrium temperature? Yes, Billy?
I know. It's going to be, well, this is at 100, and that's at 20. So it'll be the average. It'll be the in between. You take the two, add them up, and divide by 2. That's 120, 120 divided by 60. The answer's going to be 60, right in the middle. 60. I'm so smart.
No, Billy, that is not going to be the answer. Wrong.
I hate this. I hate this course. I'm quitting.
That's the attitude. All right, now, no, because what happens is we've got two different materials with different Pacific heat capacities, not Atlantic. Still funny, still funny. And we have a certain amount of aluminum, 300 grams, and we have, you ready for this? 500 grams of water. How got you 500 grams of water? It's 500 milliliters of water. Well, we all remember that 1 milliliter of water is equal to a gram. All right, good to know. Good to know if you didn't know that. So we have different amounts, different substances. Now, it's possible it could be 60, but it won't be. It won't be. So I doubt it. In fact, do a little logic here. Do a little logic. Where do you think the final settling on equilibrium temperature is going to be? Is it going to be closer to 100 or will it be closer to 20? What do you think?
Closer to 20?
Very good, Billy. I hope you weren't just guessing because you did have a 50-50 shot at it. Yeah, no, it's going to be, I mean, right, yes, Billy, you're correct. It will be closer to the 20 because water is like Keanu Reeves in The Matrix. Okay, water is like Keanu Reeves in The Matrix. Okay, remember, right? Keanu Reeves, bring it, bring it. That's what water does. Water says, bring it. What do you got? Because good luck changing me. I'm tough. Well, aluminum's like, ew. So this one's going to go down a lot. This one will go up some, but not a lot. It absorbs a lot of heat. It's got a lot of heat to raise the temperature of water. So we expect that the final equilibrium temperature to be much closer to water than aluminum. Well, let's find out. Okay, how do we find out? We use our heat equation. As in life, as in physics, as in thermodynamics, which is what we're studying right now, we're talking about heat and temperatures and heat movement, thermodynamics. One thing's loss is another thing's gain. That's the way life works. That's the way thermodynamics works. Energy, one thing's loss is something else's gain. So we have a loser and a gainer. Who's going to lose? Well, the aluminum is. It's going to get colder, so it's losing energy. Well, where does it go? It goes into the water, so the water's going to gain the energy. Let's write that down. Loser. Oh, nope. Loser, aluminum. There we go, aluminum, and the winner. The gainer is water. Let's put the equation in. Q is equal to M delta T Cp. So let's write that in for both sides. It's the same thing on both sides. M delta T Cp. Okay, but here's what I'm going to have to do in a problem like this. I'm going to have a starting temperature of water and a starting temperature of the aluminum, water and aluminum. Now when I have a final temperature, it's going to be different. So we're going to have a change in temperature. Now when it comes to a change, you always subtract. Change means subtract mathematically. So that means I'm going to be subtracting to get my change in temperature for the aluminum and for the water. When the aluminum starts out hot and ends up cold. This starts out cold and ends up warmer. I won't say hot, but it ends up warmer. So the initial temperature of the aluminum is going to be higher than the final temperature of the aluminum. So the positive value, we want to keep things in this equation positive. If you don't, it's going to screw your math up. It's going to screw it up, trust me. You need to keep the change in temperatures positive. So to keep it positive, the initial temperature for the aluminum is greater than the final temperature. So over here in my equation for the aluminum, I'm going to write in for the delta, the change, the subtraction, the T initial minus T final. Because that initial temperature of the aluminum will be greater than that final equilibrium temperature, and I need to keep these values positive in order for the math to do its job without messing it up. You can do it if you switch it, but then you got to switch other things, and I'm not even going to go into it. Not even going to win it. No. Let's do this. All right, Cp equals M delta T. Now for the water, the final temperature is going to be greater than the initial temperature because the water is gaining energy. So we switch those. So the TF, final temperature, to keep things positive, goes first like that. All right, now we've got our equation. That's our working equation set up. Let's crank it out. Let's find. There's a lot of good, there's more algebra in this problem than there was the last one I did, and on the video, right, the last video. So that's okay. You can do algebra. I have faith in you. Each and every one of you. I have faith in you. Okay. So let's go. Mass of the aluminum. Now I'm going to use kilograms. So 300 grams is 0.3 kilograms. The initial temperature of the water is 100. The final temperature, we don't know. That's what we're trying to find out. We're trying to find out that final equilibrium temperature. So that's TF. The Cp of aluminum is 900. The mass of the water, 500 milliliters. It's 500 grams. All right, 500 milliliters, 500 grams. So 500 grams. Now 500 grams is 0.5 kilograms. So 0.5 kilograms. The final temperature, so I'm trying to find the initial temperature of the water. This is the water side now, so we got to put the water information in. And for Cp of water, 4190. So there's my setup. Now my calculators aren't working. Yeah, one of them kind of crapped the bed and it gives me all kinds of funky things on the screen. This one actually is from 1986. Sometimes it works, sometimes it doesn't. It's solar. Okay, I'll get it into the correct mode. The correct mode, modem operatum, and this is annoying. Okay, hang on. Mode 9, get in degrees. That's in grade. No, that's not it. I know. You're bored. I get it. It's still not. Come on. There we go. Got it. Okay, it's in degrees. Let's hope it works. Sometimes it still doesn't work. That's all I got, though. That's all I got. Okay, beggars can't be choosers. All right. Do the math. Well, 0.3 times 100, I don't need this for that. So that's 0.3 times 100 is 30, right? So 30. So 30. Oh, you know what? I'm not going to distribute through yet. Actually, the way I'm going to do this, I'm going to multiply those first, then distribute through. Then I'll multiply these, then distribute through. You can do whatever you want. It's America, but that's the way I'm going to do it. So 900 times 0.3 is 270. 100 minus TF equals 0.5, 4190. So half of that is 2095. 2095. Is that right? I'm going to double 2095. So my brain is tired. I know I had coffee. Yeah, that's right. And then TF minus 20. Okay, so I multiplied those. Now I'm going to distribute, okay, I'm helping you through the algebra. Some of you might have forgot this, okay? You don't remember algebra. Well, I'm here for you. I'm here for you, all right? So 270 times 100, 27000 minus 270 TF equals 2095 TF. Woo! Minus, well, 2 times that and add a 0. Well, 2 times that is actually back to 49, 4190 at a 0, so 41900. All right, that should be right. Check my math, okay? All right, if I get it wrong, you can tell me in the comments section. Go ahead. You can tell me. I can take it. Okay. Add like terms. So add the TF to this side. So let's see, 270 plus 95, that had to be 3, 2, 3. I'm not. I'm just not going to. I'm tired, okay? I'm tired. I'm Firestone, I'm Goodyear, I'm Michelin, okay? I'm tired. I'm getting tired. Firestone, Michelin, tired. 2365 TF. Okay, then I'm going to take this 4190 and add that to both sides. So 4190 is 0, 4190 over here. So 4190, that's going to be 0, 0, 9, 8, 6. All right, if I did the math right. Then, finally, I'll divide by this to get TF, and let's see what we get. See if our answers will make logical sense. All right, so what do we got? We've got 6, 8, 900 divided by 41, 900, and no, I'm looking at the wrong line. I need sleep. Sleep, so good sleep. Let's see, 6, 5, bam. And I get 29.1. Where are you there? 29.1. And let's see if that makes sense. Hopefully it'll make sense to us. 29.1 degrees Celsius. Okay, does it make sense? Is that number between 20 and 100? It has to be between there. Answer, yes. All right, got that going for us. Is that number closer to water than it was than aluminum? Did the water increase the least amount? Yes. Does that make sense? Yes. Water can absorb a lot of energy, and you know, it resists changing its temperature until you pump a lot of energy into it. So yeah, water, like Keanu Reeves said, yeah, what do you got? You raised me by 9, but I lowered you by like 70. So water, I win. Water wins. So that would make sense with that problem, and that is how we do what's called a temperature equilibrium problem when we mix together two things at different temperatures. All right, that problem down. We'll see you soon.